Is it on? It should be on. Okay. As I was saying, I'm really thankful for the opportunity I've been given. I've learned a lot today. I've had very interesting conversations. And thank you for taking the time to learn about the things that we do in the lab. When I look back and I see the title in retrospect, I think I've been a little bit too technical. But let me bring this down to you. We're going to be talking about a special class of color centers, and I'll explain in general what color centers are in a minute. But we're going to talk about a particular class of color centers that are called the NV centers in diamond. We're going to be focusing particularly in sub-diffraction clusters of NV centers that we're going to investigate via optical and spin spectroscopy. So that's what the talk generically is about. And for the younger in the audience, I have to say that, well, color centers have been known for, I don't know, countless decades. And for a long time, I guess, well, at best, they were like a very interesting, though fundamental curiosity. Worst, I would say they were more like some complication for practical applications that you'd like to get rid of. And things kind of started to change, I'd say, beginning of the 2000s or so, mostly because there were, by that time, there were optical techniques that were introduced to to probe these color centers individually. And the moment you did that, it became clear that there were very strong analogies between color centers and atoms. As a matter of fact, you can think of color centers as a trapped atom inside a solid. For many practical purposes, that's the right way to visualize it. And the Hamiltonian that describes one system and the other are or have many similarities. So it's not a coincidence that people refer to color centers as artificial atoms. And that's precisely the reason why color centers are very much at the center of the second quantum revolution and all these applications that I've highlighted there. It's not just quantum information processing, broadly understood, but there's also, and perhaps more importantly, all the applications to quantum sensing that mostly come from the fact that now you have these color centers, these atom-like systems that you can grab literally through the material they are in and move around and use them, for example, for different forms of microscopy. And we've done some of it in the laboratory. Unfortunately, I won't be talking about that today. Now, if you ask me, and with my training in physics, I think that, yes, all applications, and especially in quantum, are great. But my main enthusiasm on the system since I first learned about this was the multiplicity of degrees of freedom that converge in a unique system. You have photons, and color centers essentially are systems that emit light, and so that's the connection with quantum optics. So you certainly have that degree of freedom, but then because they sit inside a crystal, there's interaction of these color centers with phonons. And Greg, for example, knows very much about that. He's been exploiting that type of interaction. There's also the possibility of changing the charge state of oftentimes, not always, but oftentimes. And today, the NV centers that we'll focus on have that feature specifically. And again, a fraction, but a pretty significant fraction of color centers have a spin that you can then address optically, learn about optically. And so it's mostly about these two degrees of freedom that the talk today is going to be focusing on. Now, when we bring in the spin, now color centers automatically become an example, an illustration of a spin qubit. And again, for those not familiar with the subject in general, I have to say that spin qubits form a much broader set. I mean, without trying to be completely exhaustive here, but there's what I would call gate-operated qubits. And examples are impurities, most notably phosphorus in silicon, for example. There's also the quantum dots, although there's quantum dots that you can address optically as well. There's the category of molecular qubits. It's a more recent direction that I think, quite honestly, is very exciting, and in particular, very exciting to chemists, because chemists can use all these tricks that we physicists really don't know much about to create and make them operate in regimes that are complementary to what we can do in color centers in inorganic systems. And very recently, well, okay, I'm citing this reference just because I'm familiar with Ashelom's work, but I've seen very recent 2026 back-to-back papers come out in Nature talking about spin qubits in proteins that obviously have sensing capabilities that otherwise, are pretty difficult to emulate with nanodiamonds, for example. There's, of course, yes, this category of color centers, and the NV center in particular is one such example, but we have others, silicon carbide, color centers in silicon carbide and in silicon. There's the special group of rare earth ions in garnets that have also been the focus of a lot of work, very exciting and interesting work. I would actually argue that there's another category of defects that I would call color centers in 2D materials. Certainly, hexagonal boron nitride is one such example. And yes, still we're talking about semiconductors. We're talking about levels inside a gap. But the type of behavior, because of the proximity, the inherent proximity to surfaces, and then the type of applications that you can think of are really very complementary. And so that's why I think there's I would include them in a separate category. Now, this is a group in Argentina that I grew up with. It has some comedians, and they are very good musicians at the same time. And this comment came about, some over-the-top campaign run by the government those days. But I listed it in here because it reminds me of the rationale that sometimes I hear when people talk about color centers and NV centers in particular. Yeah, you see, the field is too crowded. It's already a lot that's been done. I don't have much room in them. What I'm going to show or talk about today tells you that, well, that's at least partly not true, that there's still quite a lot of interesting things, in my view, to do. So I've been talking about the NV center multiple times without introducing it. You have to imagine the diamond lattice, or carbon, but now one of the carbon sites replaced by nitrogen and sitting right next to a vacancy. This is the energy diagram, and here you can see the connection with atomic physics right away. This is what we would call, say, the ground state, which in reality is a triplet, and then the first excited state, which is a spin triplet. But in reality, this excited state is an orbital doublet. So essentially, every level in here is degenerate at room temperature. Now, what happens at room temperature is that degeneracy is more dynamic than real, because there's some averaging that takes place. I won't get into the details just for brevity, but let me just say that if we lower the temperature to just, say, for example, for reference, say, less than 10 Kelvin, what we have is now the splitting, and therefore the appearance of 6 levels in here. So throughout the presentation, we're going to be focusing on optical spectroscopy between this level. We're going to distinguish what we call cycling transitions. These are transitions that start from populations here in this MS, or say spin 0 state within the ground state manifold, and take me to the equivalent spin 0 or near 0 levels in the excited state. These we call cycling because if we start here, we can maintain this laser light going for comparatively long times before the spin flips. This is not what happens if, for example, we start from these states MS plus minus 1 in the ground state, because the moment we excite them, they are going to, or very quickly actually, they are going to change the spin right away. So these two, which remember is EX and EY, and they are going to be these are the two main transitions, but then in total you have transitions overall. Another thing that we want to keep in mind in here is that if we crank up the laser intensity sufficiently, what can happen is a two-step, one-photon process where you first excite the NV to the excited state manifold, and then a second photon arrives while the system is there and takes the extra electron in the negatively charged state, which is the charged state that we mostly focus on, and then ionizes. And I know that that word may be confusing. By that, I'm going to mean we take away that excess electron and we put it, in this case, into the conduction band. So we make a transformation from negatively charged to neutral. So let me give you a picture of roughly how this all works. And so this is confocal microscopy of a bunch of NV centers. We can go and do optical spectroscopy on one of them. This is the type of optical spectrum that we will collect. Those two peaks that you see there are the EX and EY transitions that I was referring to before. Here's an interesting thing. When we go to other NV centers, we can do the exact same. But what you see immediately is that the spectra are different. And we're going to get back to that, but that happens because of changes, electrical changes in particular, in the environment. Now, the fact that these optical resonances change frequency is pretty important because, for example, it gives us the opportunity to image individually these color centers just by choosing a particular excitation wavelength. So we'll get this one if we are exciting that particular peak, or that one if we're exciting that particular peak and nothing else around. And the same applies to the rest. Now here also a technical comment just for those of you not used to working under these conditions. What I want to emphasize is here the frequency shift represents the shift relative to the laser frequency, and we're using not super narrow but quite narrow laser excitation. So compared to the standard laser, this pointer, for example, we're using line widths that are on the order of, say, 500 kilohertz or so, and that's the reason why we can actually reconstruct this type of do this type of spectroscopy that normally, with a standard laser you wouldn't do. This here is just to show an intro example of these ionization that I was referring to earlier on. I won't get into the details of the technicals of the sequence that we apply to demonstrate that. But this decay in here is demonstrating our ability to choose a particular color center and then change its charge state, which will translate into a change of the fluorescence that we see over time. And this, of course, will be dependent on the power that we use, although because this excitation is resonant, you can go with super low power in the order of even less than a microwatt and get that color center to ionize, to change charge state. Now, that possibility of addressing individual color centers just because they have different optical resonances means that you can apply the same type of selectivity when it comes to color centers that cluster in what you otherwise would think is an individual NV center, because this is diffraction limited, yet that particular spot contains more than one NV. In this particular example that I'm showing, there's two NVs. And here, this is something that we can see because if we do optically detected magnetic resonance, or DMR, of that site, what we find is a collection of 4 peaks. And if you remember in the energy diagram that I first showed, the ground state has 3 levels. That corresponds to effectively 2 transitions. So there's 2 transitions per NV center. The fact that we have 4 peaks in there, or dips in there, means that there's 2 NV centers at that site. That is also some information, the same information we can extract from optical spectroscopy. It's not straightforward to see first, but sorry. I think I'm missing probably a slide that I wanted to highlight. But if we focus our attention on this pair of peaks, the 2 appear here. But when we apply microwave that we make selective with one of the transitions, we can make that particular peak go away. So if the microwave is resonant with NVA or NVB, we'll have one or the other show up. And this translates very clearly when we examine those 2 peaks. So that's an easy way to confirm that there's 2 NV centers. We can use also make use of the good signal to noise that we get, and then do the equivalent of a super resolution microscopy to confirm that these 2 NV centers are separated by 90 nanometers or so. And so now if we focus, say, on this side of the spectrum, and we have one dip for NVA and another one for NVB, here is what we can do. We can now set the optical excitation to be strong enough to ionize selectively one NV or the other. So this is when both NVs are negatively charged and both have those resonances. But then this is what happens right after we've ionized NVA or NVB. One of the 2 dips disappeared, and then the other one is the one remaining. Now we can extend this to clusters that contain more than 2 NVs. We've done it for up to 5 inside that same diffraction limited spot. We're going to be discussing about clusters with more NVs soon enough, so I'm not going to show that. But something that I briefly wanted to digress on was that if we were to move to a concentration of NV centers where so high that we can no longer separate the spectroscopy that comes from one or the other, something that's interesting is that we can choose. Here we have an inhomogeneously broadened distribution of resonances. We can simply choose a wavelength to selectively change the charge state of the NVs at the particular wavelength that we've chosen, here denoted as these 33.5 gigahertz relative to the reference frequency. We can choose another one, for example, and then change the charge state in some different pattern. And we can continue doing that and then superimpose on that same optical plane different images, in this case, say different patterns that simply come from the ability of selectively addressing these homogeneous, heterogeneous distribution. And when it comes to, this is not something that I'm going to elaborate much on, but I simply wanted to bring up the fact that if it comes to optical storage and as an optical memory, I think that there's untapped opportunities in the sense that if you think of the number of color centers that you can pack in a 3 millimeter by 3 millimeter by, say, 200 micron thick diamond, which is the standard size, it really becomes astronomical when you think about it. So the ability to store information that way is something that potentially, has some use. Now, something that I didn't mention is that if, let's say, we focus on a single resonance, on a single optical resonance, and we repeat the measurement of that optical resonance multiple times, this is the sort of results that we will get. Each of these spectra corresponds to one frequency sweep. And you see that the resonance is always there, but then the frequency is moving around. And this is a phenomenon that is, don't get me wrong, is well known, has been known for decades. It's called spectral diffusion. The problem becomes even more apparent if instead of just having one line with a single NV, we go to a cluster that has many NVs within that same sub-diffraction spot. And so this has been well known, as I said, and most of the time it becomes a complication. And as a matter of fact, this huge spectral diffusion is the one reason why people first doing earlier demonstrations of spin photon entanglement in NV centers moved away from NV centers to other color centers that are less sensitive to this type of diffusion. It's precisely this, because this diffusion essentially means that the photons that come out won't be identical. And so that creates complication in entanglement. We had an idea. And in retrospect, I think the idea looks as bright as this sentence over there. But well, maybe I'm just too harsh. I'll let you guys judge. So the idea comes from the following realization, that when we illuminate this sub-diffraction spot, essentially what we are having is not just a collection of NV centers, but there's also other coexisting charge traps in that same volume. And it's these charge traps that are going to change charge state, and by changing the charge state, the effective electric field that a particular NV is experiencing is moving, is changing over time. And that's essentially the cause behind this spectral diffusion that I was describing before. Now, what happens with the particular case of the NV center is that the NV is so well known that you can now model and calculate very precisely how the excited and ground state manifolds change in the presence of either a transverse field, which is shown here, or a longitudinal field. I'm not showing it, but it essentially translates into this midline in here in the excited manifold moving up or down. And by the way, when I talk about, say, transverse or longitudinal, what I mean is transverse or longitudinal, orthogonal or parallel to the NV axis. That's what it means. Now, this field I refer to a delta field because it could be a strain and it could be also electrical field. Actually, the Hamiltonian is identical for both, and you cannot discriminate, at least just based on the Hamiltonian itself. That's why I refer to this as delta field, but in general, we can think of it throughout the rest of the presentation as an electric field. So now let's say that we have a particular NV center, and each of these branches in here corresponds to the particular set of levels in the excited state manifold. So we have 6 in here if we count, and these are the 6 that we have from before. Except that at this point, this separation corresponds to a particular transverse field, and there's an associate longitudinal field that goes in where these overall, the center of gravity, if you will, of these manifold lies in the spectrum. So in essence, what we can do is out of a spectrum for every NV, we can derive the transverse and longitudinal components of the electric field. Let's think of it that way. So now let's go to, in this case, a sub-diffraction cluster that happens to have 3 NVs, A, B, and C. And here is if we do repeated spectroscopy, this is the spectral diffusion that I was talking about, now seen from top. So out of each NV, as I said, we can extract delta perpendicular and delta longitudinal. And what we decided to do is we decided to plot them in a way where we correlate one with the other. Perhaps, my background, my original training as a PhD, it was in nuclear magnetic resonance. So this type of correlations, 2D representations, is something that is very natural, very usual in that community, and that's where the inspiration came from. And what you see immediately here is that this is not a uniform distribution in the sense that then you start identifying islands or sections of these two-dimensional space where things start clustering. And this essentially starts talking about discreteness in the changes that we see, that we can perhaps more clearly see with this other example. So we move in here from NVB in the other example to NVC. And what we see here is this collection of clusters. It turns out that we can model this collection pretty well if we assume that there's one configuration where this particular NV center is surrounded by neutral traps, and then another one, or let me put it this way, a single color center surrounded by 3 traps that can be either the 3 of them can be, say, neutral, or one can be charged and then the other 2 neutral. And this, the one that is charged can go from this trap 1 to trap 2 to trap 3. This that you see over here corresponds to rings where, for this particular configuration of delta longitudinal and delta perpendicular, this is where the source of that electric field can be. And these are the 3 rings, each of them associated to the different charges, or actually clusters modeled over there. So we can tell some more and actually indirectly confirm the validity of this model because, as a matter of fact, we can say that all 3 traps are located pretty much on the same plane. Why? Because if we take, say, for example, we charge simultaneously trap 1 with trap 2, what we can now predict is the occurrence of a cluster over here with about 1.7% probability at a location that matches that one over there quite well, both in position and in percent. The same we can do if we were to, say, populate trap 1 and trap 2. Again, we get a cluster that matches what we observe here. And then we can do the same with 2 and 3. So we predict now this cluster appearing with the same type of probability. So in the end, we are left with a distribution that agrees reasonably well with our distribution in here. And the fact that we can vectorially add longitudinal and transverse components of different traps is what essentially supports the notion of all three of them roughly lying on the same plane. But let me give you another example. Let's now focus on a cluster where in reality what we have, this is how the diffraction limited image of that cluster looks like. What we have here is a zoomed image where we are indicating the positions of all 4 NVs that lie within this cluster. The size of the radius is our uncertainty in terms of where, optical uncertainty in terms of where these NV centers are located. So unfortunately, it doesn't show up very clearly here on the projection. But believe me when I say the following. So if I look at, okay, so we have so D, F, G, and E, okay? E we won't care much about because we'll see it's not coupled, but the other 3 are. And so now let's start by focusing on F and G that are the closest. So what I was saying before is that every time this guy, line in F, shifts to the right, this guy, NVG, essentially has a peak that is absent. And this is what these arrows indicate. And if I was to actually now correlate the delta values for NVF, perpendicular or transverse and longitudinal, what we would, and then correlate with the charge state of NVG, what we see is a perfect match. We see that this separates into 2 groups that correspond to what the charge state of NVG is, meaning we ionize NVG, and then automatically we change the electric environment around NVF to the point that the NVF reports a spectral change. That we can actually do deterministically. If, for example, we start with a situation where we have F and G both negatively charged, and we look at these spectrum, and now we focus, say, or we tune our laser to be resonant with one of the transitions of NVG so that we ionize it. Now we collect the spectrum again, we see that the peaks corresponding to NVG are gone. But now if we look at NVF moved by about half a gigahertz or so. If we were to do the exact opposite, we start again with F and G negatively charged. We come with our laser, we ionize NVF, and now it's NVG that moved, in this case by almost 880 megahertz. By the way, there's an asymmetry between the two because there's a bias field in the back that acts differently. We can talk more about that if there's an issue, but that's essentially the reason why the change is not the same for both. So now that we have F and G interacting, the question is, okay, what can we say, for example, about NVD, which was this one over here. So let's correlate, for example, delta in this case, we'll correlate the longitudinal field observed by NVD with the longitudinal field observed by NVF. And what we see is that there's, again, two clusters. The clusters are actually created by NVG, which acts here as a third classifier. But the bottom line is that if we average this cluster over here, we end up with a shift for NVD that is different from the average that comes from this other thing, from this other set. And so this essentially is telling us that NVD is acting with, is being coupled to NVG, because the charge state of NVG is enough to create an average move of these longitudinal component of the field. Essentially the same you can say if you were to look at the transverse component of the field of NVD. And effectively you can say the same if you were to look at now NVD acting or responding to the charge state of NVF, not NVG. But let me show you, that in a little bit from a different perspective. So I was saying that the coupling between NVD and the other two is by comparison pretty weak. And so this is essentially a demonstration of that point, because if we were to correlate or try to correlate the longitudinal transverse components of NVD, we see that they lie all over the place. But here is the thing. I mean, the confusion comes from the fact that it's not just G or F that are ionizing. There's everything else that is also contributing. So those changes, however, we can somehow slow down. We can more controllably dominate, decide on the charge state of F and G. And so one thing to go around this problem is we will compare then the shift that we see between two consecutive observations of the same spectrum. Not just, the entire set, like the way we've been doing so far, but just one immediately after the other, with the idea that then the environment didn't have time to change so dramatically. So then the change is going to become then mostly defined by the charge state of the color center that it's interacting with. And this is how you can improve quite substantially the resolution. So this is a cluster that appears when both F and G are negative. But then if one of the two ionizes, say this one now becomes neutral, or F becomes neutral, now you have different clusters, and these essentially demonstrates that D is actually interacting with both F and G. So now that we have these three NV centers all interacting with each other, and we know now by how much, what we can do is, for example, we can take the two that interact the strongest and calculate the region in space where NVD is supposed to be at according to, say, NVF. And then do the exact same for the other color center. And then what we see here is that the two rings that we calculate coming from either one or the other intersect at this particular point. And at this particular point, then, we are now determining the position of this NVD that is interacting with the other two. In other words, this is a sort of GPS-like type of triangulation where you use the signal that is recorded by two NV centers to triangulate in 3 dimensions unambiguously what the position of these third interacting NV center is. We can actually, I'm running out of time. I won't explain the details, but you can apply the exact same idea for dark traps, not just other NV centers. Say traps that will have some charge that doesn't necessarily fluoresce. And we can actually, by doing this type of triangulation, determine what the charge sign is. So we can know if that charge is positive or negative, because in one case we would have intersecting rings, and in the other case we won't. And so, a long story short, essentially we are able to derive, just out of these spectral diffusion, a three-dimensional map of where, in this case, the 3 NVs plus 2 dark traps lie in this sub-diffraction volume. So we can compare the maps that come out when projected onto the optical focal plane with the optical image that we have, and we have a pretty good agreement. Not exactly, but pretty good. Again, the distances that we're talking about in here, you can see right there, and it's something in the order of at most 150 nanometers or so. That defines in practice how far away we can go and still and do this sensing. Oh, and by the way, this was a paper that came out just literally, I'm not exaggerating, a day or two before we were about to submit ours. So we were scooped good. But it says the exact same. But it's always a good thing to have, an independent confirmation. I'm saying this because, yeah, that's what happened. So by the end of these tests and calculations, we were having all kinds of different ideas that we still, want to carry out, but we sort of postponed. And this was because at the time we got a new toy to play with, which came in the form of a EMCCD camera. So this is essentially the type of measurements that we can do here. This is not what the configuration that we use now, but it's what we used at the time. And essentially what we have is these red beam bouncing off the back surface of the diamond and then spreading over an area. That's going to be our field of view, and we're going to collect images from all NVs that are within this section of the crystal over here. Now, these images are going to be spectrally sensitive in the sense that this is the red beam, whose actually frequency we can change. And so every spot in this image corresponds effectively to a spectrum. And because we can do that multiple times, then essentially what we end up with is a 4-dimensional data set where you have the 2D positioning, then the spectroscopy, and then the fluctuations over time. So this is how it looks like, and this is such an example of a 4D data set with several NVs in pretty good proximity to each other. So again, we can't see it very clearly here, but I'll show you a little picture, if I can, actually. So what you're seeing now is the image that is being recorded as we change the wavelength of the red beam over here. And what you see is each spot lighting up multiple times. For every resonance, you have a bright spark. And you can do that for all these field of view simultaneously. This is what we repeat to produce a 4-dimensional data set. And I want to actually show the real actors here. I'm more like the messenger, because this is not, maybe for others in the audience it's trivial. Well, experimentally for us it wasn't, and it's not so simple with NV centers and the level of fluorescence they have to capture this type of processes in a single run with such clarity. So this was a pretty nice enabling tool that we used for the experiments that I'm going to describe next. And with this, I hope to to conclude. So let me show you the protocol, because if you understand the protocol, then you'll understand the main idea. So what we first do is here we'll use the same type of configuration, but instead of the red beam that comes next, we're going to be using the green beam. And I call these charge and spin initialization. This green beam is not tunable, is not narrow band, it's not narrow line width. It's just standard laser at 532 nanometers. And what happens at these 532 nanometers is that you actually initialize preferentially the charge state of the NV center into negative, and also the spin state into ms equals 0 in the ground state. So that's what the purpose of this pulse is. And then we're going to go through a cycle where we tune our laser and we do a wavelength or frequency sweep of that same spot here, moving the resonance or the frequency of that tunable laser. We're collecting an image in the process, and then we'll do a selective excitation of one with green light of one NV centers in a larger ensemble. Now, this is actually something important for what comes next. I already mentioned early on that if we use red light strong enough, we can actually make the NV minus transition to NV 0. Well, if we illuminate with green light, you can also do that. The same process applies. But with green light, there's also an extra degree of freedom. Green light also excites the neutral version of the NV. And again, through a two-photon process where you first excite the NV0 into the excited state manifold, and then you inject an electron from the valence band, you can land from NV0 into NV minus. So essentially, green light means that you can, illumination with green light means that you can charge cycle the NV from neutral to negative and back. And if you think about it, every time you do that cycling, you're injecting charge into the medium. Those charges have to go somewhere. Now, this is one initial demonstration of that charge cycling that I was talking about. So we're focusing, let's say, here in this particular NV center that we'll refer to as the source NV, hence NVS. We're using our protocol in here to monitor the charge state of the NV as we change the green illumination time. And what you see here is the charge state of the NV center cycling as we continue applying the this green light. And we see that as a change in PL because our microscope is configured so that we are sensitive to NV minus light, but not NV 0 light. Okay, so that is what creates the charge cycling. Okay, so now instead of focusing on the source NV, let's focus on some other NV. Let's say this one over here, which is about 25 microns away. We know because we've initialized that guy to initially be in the bright state, that is the negatively charged state. But now you can think of the NV as it charge cycles as a charge pump. You essentially use it to inject charge into the valence and conduction bands. Now, the electron that you inject into the conduction band is going to be coulombically attracted to an NV minus. But you see, the converse is not going to happen because if you have a hole, the hole is going to be attracted to the negatively charged NV, but an electron is not going to be attracted particularly by a neutral NV. So essentially, it translates into now being able to capture a hole that is being generated by this guy over here. And this process is something that we can capture as we extend the green illumination time. So at some point in time, you see a big drop in the PL that essentially indicates a capture of a hole generated by that NV. Now we can repeat that multiple times and see how long it takes on average for that NV center to capture that particular hole. And so we get a collection of traces like this that last for different times. We can build histograms out of this and then determine what is the average capture time for that particular NV. And because we know how much charge is we are injecting per unit time, and we know how long they are, how far away they are, we can then determine the capture cross-section associated to that particular NV. We can do the exact same with some other NV, let's say this NVB, where we see a substantial change in the capture rate over here. As a matter of fact, we can do it for every single NV in the field of view in here, and then record a map of the capture rate as a function of position relative to the source NV. Perhaps we can see that more clearly in this graph where yes, there's quite substantial dispersion, and I'll explain in a minute why. But overall, you see a trend that goes like 1 over d squared, which is, understandable if we imagine now these carriers propagating sort of from a point source and isotropically. And there's not much reason to think otherwise in diamond, which happens to be quite isotropic. Out of these measurements, we can determine, as I said, the capture cross-section. And this capture cross-section, something that you'd expect is the capture cross-section to be the same for all NVs. And the trend in here is quite was pretty interesting early on, because what we found was that this capture cross-section, yes, there's the dispersion that we expect, but then there's also this trend to grow as the distance increases. And so then the question comes, why is it that the farther I am from a source, the capture cross-section goes up? We started to understand this when we compared, when we started seeing the spectroscopy specific for comparing the spectroscopy from different centers that had different capture cross-sections. And here I'm showing an example. So this one is what I would call, say, a normal NV center. And there's a sort of exponential decay in that histogram that translates, we can define what we call an instantaneous capture rate. And this instantaneous capture rate remains kind of constant throughout the green illumination time. And if we see that, how that translates into the optical response, we see that the PLE, the resonance that we're interested in this case, remains kind of uniform, kind of stable. There's some spectral diffusion, but it's nothing major. Now, let's look at this other NV where you see the behavior is not quite normal. It's not what we'd expect. And again, if we were to calculate this instantaneous capture cross-section, this points to a situation where the capture cross-section is increasing as a function of the green illumination time. And what we've seen is that this trend correlates with how this PLE peak responds over time. So you see that systematically, every green horizontal line here means, repeat of the same protocol. And so every time we start from somewhere over here, and then the line drifts, let's say, to the left in this case, systematically. It's not, the type of discrete jump that we were talking about. This is more like a smooth drift in one direction, and quite reproducibly. This in no way the only instance. Here I'm showing two alternative examples. And the way to rationalize it is that essentially there's some group or cluster of traps that somewhere lie in the way between the source and the target. And it's only until you somehow populated these traps with the charge they want to have in this shower of carriers that they are exposed to, that ultimately the system comes to a sort of equilibrium, and then the transition takes the final wavelength or frequency that it's supposed to have. So this gives us an idea. So compare this situation where now we use this wide field green illumination we initialize. When we use this green illumination, we're creating all kinds of ionized traps around the NV center of interest. And so the result is that every time we go through this protocol and we redo the measurement, we'll have this big spectral diffusion that I started with. But then let's imagine an alternative scenario where you now start you use some other source NV. It's not the target NV or the probe NV that we're interested in. Some source NV that is far away and that we use as a source to create all these carriers that will propagate and ultimately neutralize the traps that lie in the path. So for example, if a trap is negatively charged, then that one will preferentially collect a Hall. And the opposite will happen if it's positively charged. And so the result is that we're going to end up with a situation where we have the probe NV now surrounded by a bunch of neutral charges, not randomly charged traps. And so look at what happens when we do the spectroscopy. Now the spectral diffusion is gone. And this is, again, because the environment is now controlled to the point that now the PLE spectra comes reproducibly clean. The last thing I'm going to mention is that if we compare the capture cross-section of the same NV and this protocol or this other protocol, what we find is that, you see, this guy has a capture time an order of magnitude longer than this guy. As a matter of fact, if we actually go to NV centers at different distances from the source, that's always the case. So this example that I'm showing here corresponds to these two guys over here, right? But then if we go farther away, we see this other thing, that the capture cross-section increases in both cases. In this case, however, it increases even more. And now notice that the capture cross-section in here corresponds to a capture radius of 200 nanometers. It's a 400 nanometer diameter capture cross-section that I think is gigantic in terms of if we do comparisons with what's being measured, for example, in ensemble measurements that's been the standard so far. So I can explain why on what these 200 nanometers involve or what the consequence of that could be. But let me just give you a hint as to where this growth comes from. And what we think is happening here is that these carriers that we're injecting essentially are just too hot. And so they'll take some time to thermalize, to come down to 4 Kelvin. And if we run Monte Carlo simulations, we can see that it takes about tens of microns until it finally cools down. When it cools down, then the capture can take place more efficiently because the Rydberg orbit that is being created during the capture process now it becomes effectively larger. You have just to compare the energy that is involved in the energy needed for making the capture stable. So I can clarify that later if there's interest. But I'm going to conclude with this because I've taken more time than I thought. We've talked about reversible charge control, a non-destructive charge readout of individual NVs with sub-diffraction resolution. We use a spectral diffusion in a way that allowed us to gain information about locations of traps and NV centers in three-dimensional space. We multiplexed detection over multiple NVs to learn about the formation of space charge fields. And then we applied this understanding to control the environment and then minimize spectral diffusion by neutralizing coexisting traps. And well, here I'm concluding with just a general thought about the opportunities, in particular charge transfer, and then the creation of Rydberg states that are things that I'll be happy to talk about later if there's time and interest. I want to conclude with simply acknowledging and thanking my group members and collaborators, particularly Tom and Richard, who were the leaders here. There's also Jason that is not in this photo, but was also involved in some of these measurements. Yes, this is some advertising in case there's people interested and graduating anytime soon. I couldn't help. I was visiting Cornell, right? So, you know, I had to do this. And, well, I'll leave you with perhaps a little bit cruel, but a pretty good demonstration of Argentinian humor here. Thank you very much.
So thanks for a great talk. So on the cluster work, the fact that they were all in a plane, each of the cluster of three that you were looking at, was that plane a growth plane? And you know, can you say anything about like the sample type to understand why they might all be in one plane?
So you're talking about the traps, right? Not the NVs.
Yeah, that's exactly what. So I guess, I mean, if I have 3 points, that just defines a plane, so that's trivial. But I'm wondering if there's an underlying.
We haven't done enough statistics to honestly answer that. What we have done, though, which goes along the lines of that you are implicitly indicating, is one observation that we made early on was that, you know, if you just spread randomly the NVs in a diamond, your chances with this type of NV concentration, your chances of finding 2 NVs within a sub-diffraction spot are like pretty much winning a lottery. And what we realized right away is that, you know, this is way more common than usual. As a matter of fact, this is one example where we did statistics on different crystals that compare chances of having, say, single NVs or doubles or triples if it's a naturally or, say, random distribution, or if, sorry, this is the simulated in red, or if it's measured. And what we systematically find here and here is that chances are that the NVs are going to form clusters. So that already indicates that you know, there's a preferential, there's some bias in the formation. Now, where that bias comes from, whether it's because vacancies like to, so the nitrogens are already naturally clustered, and then it just the formation of NV center reflects that. That's one option. But we could think of others, and it's unclear at this point exactly what that is. So all that is certainly within the realm of possibilities.
Is internal photoionization independent?
Ah. Well, I'm glad that you actually made that question, because what you are one of the few people who actually think like me because of the background. And certainly that's our immediate horizon. So what we've done, I mean, the thing is that the reason why I've been postponing answering that question is not because I didn't find it interesting or whatnot. It's just that we didn't have yet the right tools to address it. And one tool that was critical that now we've sorted out is our ability to now selectively address NV0. Because if we now want to demonstrate the spin selectivity and we want to have a pretty good capture cross-section, what we want to inject is spin polarized hole, not an electron. And electrons we can polarize pretty quickly and then, use the standard protocols to ionize. And I'm pretty sure we inject spin polarized electrons. But then comes the question, how do you probe that? And so because we actually have these capture of holes, we would actually need to do the converse. We need to inject spin polarized holes. This is actually something that we are, as we speak, achieving now. So we've been able, our setup, is not a $2 million setup. And so we don't have vector magnetic field control, for example. And to split the line of NV0 so that you can now do a selective ionization and a spin selective injection of a hole, you need a strong enough field. So much of the time we've spent in the meantime has been in adapting, permanent magnet and manipulating that permanent magnet inside our cryostat so that now we can have, we just saw that splitting. So we have the yellow laser for NV0. We just have seen the splitting. And then the next stop is definitely that. I think that there's every reason to imagine that, the capture is going to have to be, if we preserve the spin in the injection, the capture has to be spin selective. And there's people who have worked on silicon before, have seen, spin selective capture. So we'll see. But I'm optimistic that we will see something interesting.
Actually,
Yeah, so both are great questions. And on our radar, I always put more on my plate than I can chew. And so, it's so certainly we haven't done this because we didn't have yet the bandwidth. But certainly those are very interesting questions. We tried and failed to address the first one of your questions, which was, well, can we do some kind of enhanced electrometry by using just the optical transitions? And one of the things that we learned the hard way that time, although we didn't push it, it was just something we were trying to see based on this same that you just highlighted, is that so this, first of all, you need to bring in the NV centers closer to the surface, because if not, you're too far away. Yes, you'll detect some macroscopic source, but then that's not so interesting. Presumably, you can detect an individual charge that is outside diamond somewhere a few nanometers away. But that essentially means that you have to bring in your NV center, put it close to the surface. And when you do that, then the number of traps that you have around multiplies exponentially. And so then the spectral diffusion that you have to deal with grows. So where do we stand now? We know that, for example, if we operate under the standards, say, NV sensing conditions, we do in the lab, say, NMR, for example. In those cases, we have NVs that are, say, 10 nanometers away from the surface. That's out of the question. We cannot, because the spectral diffusion, at least with the samples that we've dealt with, which are presumably high quality, won't allow us. But we know that if we now put that layer about between 50 and 100 nanometers below, then there's the spectral diffusion that is very much comparable to bulk. So that problem could be sorted out, of course, at the expense of some sensitivity, but that could be sorted out. However, there's the extra question, there's the extra problem that on the surface, you also have mobile charges. And you move those charges when you use your laser, you like it or not. And what happens then is that when you put in an electric field, then charges are going to go and try to shield that electric field. And so now that lowers further your sensitivity, your ability to probe those fields. So certainly there's going to be some sweet spot. There's something that we're going to be able to do, but it's going to demand more effort. As for the second part of the question, whether you can now start trying to correlate in more in fancier ways, if you will, and ideally, if you could use entanglement as a resource, certainly that's a possibility. It's an interesting one, and we haven't seriously tackled that. All these correlations are fully classical, but I think that there's room there, and work by, for example, Natalie de Leon they don't use the same tools, but goes definitely in that direction and leads the pack in that respect.